Alright, it's time for another math. Easy. So we're going to discuss well further into Newton's method on linear approximations and look at part 2 of the example series, basically where Newton's method fails, or it fails to converge, or it slowly converges. And we'll do these examples here. There's 4 total here. This shouldn't be too fast, but we'll see how far I can get into these in this video. Basically, before we do the examples, I just want to recap on the Newton's method. You can see in a video link below in the info on more detail of this, but basically what it is states is just if you have a function like this f of x and you want to approximate this root, where x is equal to r in this case, basically first thing you're going to do is pick a starting point, the approximation like x1, and then from x1 you would find f of x1, the value at the function here, and then you would use a tangent line. You just find the derivative here and draw the tangent line until it cross the x-axis. So basically once you get to this point here, because remember you're trying to solve for f of x equals to 0, and then basically what x values are. So you get x2 here, and x2 is closer to r than x1 where you started. Then you would repeat it here, you would go back down here and do this again. This would be x3 until you get closer and closer to the root here. And then with the derivative is just rise over run here, so you have a derivative is equal to, well, 0 is where the f of x value at x2 minus f of x1 divided by x2 minus x1. Rearrange this, you'll get something like this, and then if you put this into this form here, xn plus 1, so because it's an iterative process. For x3 this would be x2, so then you'll get something like this here, and then the limit as n goes to infinity of xn is just equal to the root, or roughly equal to the root here. So now let's look at example 1 here. So now example 1 basically states, explain why Newton's method doesn't work for finding the root of the equation x cubed minus 3x plus 6 equals 0 if the initial approximation is x1 equals 1. Well, let's just follow the steps here and basically write this formula here. So we know that, well, first thing we have to do is this is f of x is just equal to x cubed minus 3x plus 6. Then taking the derivative is just going to be equal to 3x squared minus 3 here. So now if we just plug into that formula, xn plus 1 is equal to, basically xn minus the f of x here and divided by f prime of x in this case here, of xn. So now, if in this case here, as you can see here, if we use this approximate x1 equals 1, basically x2 would equal to 1 minus, well, the top's just going to be 1 minus 3 plus 6, and then the bottom's going to be, well, 3 minus 3, and this is a 0. This equals to 0, so we're going to have a something divided by just a number divided by 0, so then this is not defined. Yeah, and thus basically if it's not defined here, because you can't divide by 0, so then Newton's method fails to work here. So you have to be careful when picking your approximation here, so you would have to pick something else besides 1 here. Well, let's now, that's the answer to this question. Let's look at example 2 now. So now example 2 basically says use Newton's method to find the root of the equation x cubed minus x equals 1 here for the initial approximations of x1 equals 1, x1 equals 0.6, and x1 equals 0.57 here. Basically graph it and its tangent lines at this point to see why it's so sensitive to initial approximation. Well, first let's just get this formula set up. So again, f of x in this case, well, we have to rearrange this, right? So this is going to be equal to x cubed minus x minus 1. We shift this over here so that it equals 1 in this case. I mean, it equals 0 here. And then remember, this is equal to 0 there. We set it there. So now we have this derivative. Now we just have, if you take the derivative of this one, it's going to be 3x squared minus 1 here. And then the formula we have to set up would just be, we'll just write it down here, xn plus 1 is equal to xn, the minus the top here, the f of xn, and then this is the derivative of this one. So now you could do this manually or with a graphing calculator or whatnot, or just whatnot, but I'm going to use Excel here. So yeah, I already did this problem here with Microsoft Excel. Here I set up a little table in this case, and basically have xn in this case, and then this is f of xn, which is the formula here, which is just xn cubed minus xn minus 1. And I put this table format. You can see my earlier video on this to see how to create this table, but basically then this is the derivative here. This is a function of this one here, so xn squared I made a table. You just could, but anyway, that's why it's written like this. But anyway, squared, and then times by 3 minus 1, and then xn is just a formula in this case, which is just xn minus f of xn divided by this one here, the derivative of it. And then we get 1.5 and whatnot, and as you can see, then the new one's going to be 1.5, and we keep repeating this step until we get basically f of xn is 0 here, and as you can see, it's 1.324717957 here. So this is with the xn is equal to 1. But if I put xn is equal to 0.6, and in this case here, you can see that the next value here is xn plus 1 is, or x2 is going to be 17.9, and as you can see, it's much further than this 1.34, which is the root here. And then it takes much longer to basically get it. Well, yeah, more than double the distance, or I think double here, the iterations it takes to get before it starts getting to 0. So then it gets the same value here, 1.34757. And then if we do, then I did it with 0.57. This is only 0.03 difference here from this one, and look at how far this one takes. This one goes to negative 54.16 and all the way there, and as you can see all the way over here, it takes much longer than even this one here. So if we compare them all, because the final value, these ones all iterate to this final root here, but it takes this one's much longer than all of these ones here. And now I'll explain why. Yeah, and that's basically part of the second part of the question. Basically, graph this one here and its tangent lines at x1, 0.6, 0.57 to explain why this method is so sensitive to this initial value. Well, if you graph it here, well, with Google Graphing Calculator, I graphed it right here in this case. As you can see how it looks like. So this is the initial one is 1 here, and then this one, as you can see what this value here, this one's roughly 0.57 in this case, or 0.58. So if I just draw this manually here, basically you have, this is the function here, or this function right here. And now if you were to draw the tangent lines, let's say at x equals to 1 here, because remember, this is the root. When you graph it, this, you can see it visually as the root, and this is where 1 is. So if you pick this point here, you're going to have something like this. And then you're going to use a tangent line, and then the tangent line is going to be somewhere here. And then similar, you go here, so you go back up, and then you get a tangent line above here. So as you see, it converges much faster than if you pick 0.6. Yeah, so then the next one's 0.6 in this case, or this point right here, which is the max here. This is roughly at we'll just say 0.58 or 0.58 roughly here. So then picking it somewhere close to it, because you see it's concaving up, and this one is this derivative here. This tangent line is almost like straight here, and this one is much more horizontal. And then if you put 0.6 in this case, this is the initial starting point. You're gonna have something like this, and then the tangent line, as you can see, is much further out. And then this one, I'm not sure. I think the graph goes like that, keeps going like something like that. And as you can see, it goes here. I mean, just keeps straight up there. And if you put it down here, then the derivative is gonna be, just as you can see, it's further off from it. And then when you get to derivative here, it's going to be somewhere like this. This is not the scale. And as you can see, it will take longer to iterate than this one. Slightly longer. But then if you pick 0.57, which is very close to the max here, so 0.57, and the actual, the derivative is almost horizontal here. It's almost at the maximum where the derivative is 0. Then this value actually, it goes all the way over here, and basically when you look at this one here, the second value is negative 54, which is ridiculously far away. So it keeps going all the way here, and then from this point here it will find whatever this value is here, in this case something like this. So we'll find it somewhere here, and then it will get the derivative. It's going to go somewhere like this. So as you can see, this one's going to take much farther to get closer to this. This one is concaving down, but just get an idea. And then taking the derivative. So then, as you can see, it will take much longer to iterate to get to this r here. Well, that explains example 2. Hopefully you learned from that one. Now let's look at example 3 here. Now example 3 basically states, so I'll explain why Newton's method fails when you apply it to this equation to solve for the root here with any initial approximation x1 is not equal to 0. Illustrate, because if you put 0 in, that's the root here. We're just trying to see if we can get the root by approximating. Illustrate your explanation with a sketch. So basically, f(x) in this case is equal to 3 or a cubed root, or just put x1 over 3 here. I just like writing it like this. So now, taking a derivative, we're just going to get, this is going to be 1 over 3 x, then minus 3, that's going to negative 2 over 3 in this case, or 1 over 3 x 2 over 3. And now we're just plugging into the Newton's formula here. Xn plus 1 is equal to, xn minus, well, the f of x here, and then divided by the prime here. And this is 1 divided by, you could flip it over, so this one simplifies to xn minus 3xn 1 over 3 times it by, well, this one's just going to be xn times 2 over 3, and then with powers here you can add these up. You can add these up here, the powers here. You can see my video in the info link below, basically see on power functions, how they work. Basically, if you add these up here, this is xn 1 to the 3, this is a like term xn, this is just going to be, add these up together, we're going to get 3xn 1 over 3 plus 2 over 3, and this just becomes 3 over 3, or 1. So this just equals 2xn minus 3xn here, because remember this part equals to 1. So now if we simplify this, we're going to get negative 2xn in this case. So as you see, there's a problem here, because now we have xn plus 1 is this equal to negative 2xn. So it doesn't matter what the number is, we're just going to get bigger. It's always going to get bigger here. So if you put in, let's say, besides xn equals 0, so let's say we put in 1 here, 1 for x1, then we're going to get x2 is just equal to negative 2. And then x3 is just going to be equal to, well, negative 2 times negative 2, and this is equals to 4. So you see it gets bigger and bigger here, and will never converge here. And this is an instance where Newton's method failed. So now this brings us to our last example here, and this is another one where basically explain why this function here, it's a two-part function. Well, we know that the root is 0, also explain why, but basically explain why Newton's method fails to find a root no matter which initial approximation when x1 is not equal to 0. And illustrate your explanation with a sketch. Well, this graph here, for x is greater than 0, is what it's saying. You're gonna have something like this here. This is the square root when it's greater than it, so this is positive square root x here. And now when it's negative, if you put in, let's say, negative number here, let's say negative 4, and then we're going to have negative 4. So the square is going to be positive, so this equals negative 4 here. So then as you can see, this is just the opposite of this one here. So we're just going to have a negative of this one here. So it's going to be looks like something like this. Because if it's square root 4 is going to be somewhere around, it's going to be equal to 2. Then this is just equal to negative 2 here, versus if there was no negative here, it's just going to be 2 on this case. So we're going to have something like this. And this function here is negative x. This part's straight here. Well, let's ignore this part. But basically you have something like this here. So now if we apply Newton's method, because we know that the root is 0. The root's 0 here, and just plug in the 0 in there. But then just show how Newton's method fails in this case. When your approximation is not 0. For example, if you put, let's say in this case, x1 equals 1 here. So what are we going to get from this? Well, as you can see here, the derivative is going to go down here. We're going to get some value here. But let's just first derive the equation. So xn. Actually, before the xn, we know that we just take the derivative here. F of x is just going to equal to, well, this one's going to be 1 over 2 using our power rule, root x in this case. And then, or write in this two-part one, basically 1 over 2 root x when x is greater than 0. And then for this negative stuff in this side here, we're going to get negative 1 over 2 square root negative x times by then using chain rule, it's going to be positive here. So times by negative 1. Or just make it a positive. So now with Newton's method, we're going to get two parts here actually, because we're going to get for when xn is, let's say it's greater than or equal to 0, we're going to have it equal to, or xn plus 1 would just equal to xn minus, xn minus, well, square root x divided by 1 over 2 times square root n here. And then if we just flip this over here, we're going to get xn minus 2xn times xn. Remember, these add up here. This just becomes xn minus 2xn in this case. And then this one, if we just simplify, is negative xn. So what this is saying, if you pick an initial approximation that is greater than 0, then you're just going to get the same value but negative of it. So now if we put for xn is less than 0, we're going to get xn. Here, xn minus, well, this is the negative square root negative xn divided by 1 over 2 square root negative xn. This is positive here. Then if we just simplify this, take this on the top, we're going to get xn, well, this was going to be negative minus negative, this would be positive square, we'll put a 2 here, negative xn times square root negative xn. The square roots cancel. We're going to get xn plus 2 negative xn, and then this one's going to be as well, it's going to be negative xn here when we simplify it here. So basically, regardless what function you use, it's going to be this one right here. So as you can see in this case, let's say we put in negative 2. So yeah, so you see it never converges here. Let's say let's say x1 is equal to 1, positive 1. Then we're going to have xn plus 1, or x2 is equal to negative 1 here. And then x3 is just going to be equal to negative 1, so this is going to be 1. And it keeps going on, it never changes. And yeah, so it doesn't matter what you pick. And you pick negative 2, it's going to be the same value but negative of it. So it never converges. And you can see from this one here, if this is x1 equals to 1, xn or x2, if we put the tangent line across here, this is just going to be, well, let's just say it hit here. This is at x2 is equal to negative 1. And then we just take it here and we take the derivative, it's going to be the exact same thing. So you're going to go back to this part. x1 is 1 because it's negative of negative 1 is 1. So then it keeps going back around in circles here. It goes up here, goes there, goes there, goes there, and it never converges. So then Newton's method fails in this case. Well, that's all for now. If we learn from these examples here, and we can download these examples, you can read them off and whatnot. This is the same, these examples I got from my calculus book. But anyways, hopefully you learned about this method and how it fails to converge at some areas, or like example 2 where it just slowly converges here depending on which approximation you use here. So as you get to know, because your calculator probably does this or a certain method whenever it finds the roots or graphs or whatnot. Well, that's all for today. Hopefully you learned about Newton's method, and stay tuned for another math easy solution.